Hello there, and welcome back to Relearnway. I'm really glad you found your way here tonight. Wherever you're watching from, whatever kind of day you've had, you can let it go now. There's nothing you need to do for the next little while except get comfortable and let your mind soften. Tonight, we're going somewhere quietly remarkable, inside the ordinary, everyday process of learning itself. Not a test, not a lecture, just a slow, gentle look at what actually happens when a brain picks up something new, how a memory takes hold, why some things stick and others slip away, and how, astonishingly, a baby can begin learning language within minutes of being born into a world of sound. We'll meet a scientist who once felt almost personally haunted by a single number. We'll hear about a man who spent years quietly memorizing nonsense just to understand his own memory. We'll wander past a room full of ordinary volunteers who, without quite realizing it, took part in one of the more charming experiments in modern neuroscience by learning to juggle. None of this asks anything of you right now except rest. You don't need to remember the details. You don't need to stay awake for the interesting parts. If your eyes close before we're through, that's more than fine. That's actually rather fitting, given the subject. If these quiet evenings help you unwind, a like or a subscribe helps this reach someone else looking for a calmer way to end their day. Get comfortable. Let your breathing slow. Let's begin. Here's a question worth sitting with gently for a moment. When you learn something new, what actually changes? Not what you can now do or say, but what changes inside the physical, biological brain itself. For a long time, many scientists assumed the answer was not much, structurally speaking. The adult brain, the thinking went, was largely fixed, capable of forming new memories, sure, but not of physically reshaping itself, the way, say, a muscle might change with exercise. Then, in the early 2000s, a researcher named Bogdan Dragansky and his colleagues in Germany decided to test this rather directly, using a skill almost nobody in their study already had: juggling. They gathered a group of ordinary volunteers, not circus performers, not athletes, just people who'd never juggled a day in their lives, and scanned their brains using detailed imaging. Then they taught them to juggle 3 balls over a period of about 3 months and scanned their brains again. What they found was genuinely surprising. In the volunteers who'd learned to juggle, specific areas of the brain associated with processing visual motion had measurably grown, more gray matter than before, in precisely the regions you'd expect to be involved in tracking several objects moving through the air at once. The people who hadn't learned to juggle showed no such change. And here's the part that makes the finding even more interesting. When the volunteers stopped practicing and were scanned again some months later, those same brain regions had partly shrunk back down again, closer to where they'd started. The change wasn't permanent. It was responsive, almost like a muscle that grows with use and eases when the use stops. Somewhere out there is very possibly the most scientifically significant juggling class in history, and it's a fair guess that none of the participants fully appreciated, in the moment, that their slightly clumsy first attempts at keeping 3 balls in the air were quietly rewriting a small, chosen corner of their own brains. This is neuroplasticity, the brain's capacity to physically reshape itself in response to what you practice at almost any age, not only in childhood. It's a rather lovely thing to know, lying here in the dark, that learning isn't just information passing through you and leaving a faint trace behind. It leaves an actual physical mark, however temporary, on the very tissue doing the thinking. Let's look next at how that same brain decides what to keep. You've almost certainly done this, read the same page of notes 3, 4, 5 times in a row, watching the words grow more and more familiar, feeling reasonably confident you now know the material. Here's the quietly inconvenient truth research keeps turning up. That feeling of familiarity is not the same thing as actually remembering something later, and rereading may be one of the least effective ways to study, even though it feels productive the whole time you're doing it. In 2006, two researchers named Henry Roediger and Jeffrey Karpik ran an experiment that's since become one of the more influential in all of learning science. Students studied short passages of text. Some students then reread the passage several more times. Others, instead, closed the material away and simply tried to recall as much as they could without looking. What researchers call retrieval practice, or more simply, testing yourself. When tested just 5 minutes later, the rereaders actually did slightly better, which probably felt like exactly what you'd expect. But when the same students were tested again a week later, the results had completely flipped. The group that had spent their time testing themselves rather than rereading remembered substantially more. And in a detail I find quietly delightful, the students themselves had confidently predicted the opposite outcome. Most of them believed rereading would serve them better in the long run, right up until the evidence said otherwise. Rereading, in other words, is a little like walking past a gym every day and feeling vaguely fit for having noticed it was there. Testing yourself is walking inside and actually doing something, even though it feels harder and less pleasant in the moment. There's a small, related note worth mentioning gently here about handwriting. An influential early study by researchers Pam Mueller and Daniel Oppenheimer found that students who took lecture notes by hand later showed a deeper conceptual understanding than students who typed their notes on a laptop. The thinking being that handwriting is slow enough to force you to summarize and process ideas in your own words, rather than simply transcribing everything verbatim. It's a genuinely interesting finding, though it's worth saying plainly that later attempts to reproduce the exact size of that effect have had mixed results, so it's probably wisest to treat it as a reasonable direction to experiment with, rather than a strict rule to follow. What both of these findings point toward, gently, is the same underlying idea: the studying that feels a little effortful, recalling instead of rereading, summarizing instead of copying, tends to be the studying that actually stays with you. Which raises a natural next question. If some things stick, why do so many others quietly slip away? In the 1880s, in Germany, a researcher named Hermann Ebbinghaus decided to study memory in a way nobody quite had before, using himself as the only subject and using material specifically designed to mean nothing at all. He invented what are now called nonsense syllables, small, meaningless combinations of letters, deliberately stripped of any existing association, so that memorizing them would reflect pure memory rather than prior knowledge or emotional connection. Then, alone in his study, over years, he set about memorizing thousands of these invented syllables, testing himself again and again, carefully recording exactly how much he forgot after different lengths of time. It's worth pausing on that for a moment. A grown scientist, quietly and deliberately spending years of his working life memorizing gibberish. Purely so, the rest of us might someday understand how forgetting actually behaves. There's something almost touchingly odd about that level of dedication. What Ebbinghaus found and carefully plotted has become one of the most famous shapes in psychology. Forgetting happens quickly at first. A great deal is lost within the first day or so, and then the rate of loss slows down considerably, leveling off into a long, gentle decline rather than a straight line to zero. Researchers now call this the forgetting curve. For well over a century, This curve simply sat in the historical record as a fascinating but old finding from a rather different era of science. Then, in 2015, researchers Jaap Murray and Joeri Droos decided to test whether Ebbinghaus's basic finding actually held up under modern conditions. Working with new participants, using more rigorous modern methods, they found essentially the same curve shape Ebbinghaus had described more than 100 years earlier, a rare and rather satisfying case of a very old finding standing up remarkably well to modern scrutiny. Here's the gentler way to think about all of this as you lie here tonight. Forgetting isn't evidence that something is wrong with your memory. It appears to be simply how memory works, by design, a filtering process, sorting constantly through what's worth holding on to and what safely isn't, the way a person naturally lets go of yesterday's weather while still remembering their own name. Which brings us naturally to a very practical question. If forgetting is inevitable, does it matter when you choose to review something? It turns out, timing matters enormously, probably more than most students, throughout history, have ever been taught. In 2006, a team of researchers led by Nicholas Cepeda pulled together an extraordinary amount of existing research, over 300 separate experiments, examining what's called distributed practice, or more simply, spacing your studying out over time, rather than cramming it all into one sitting. Across this enormous pool of evidence, spanning decades of separate studies conducted by many different researchers in many different contexts, one finding kept appearing again and again with remarkable consistency. Spaced-out practice reliably produced better long-term retention than the same amount of studying crammed into a single session, not occasionally, not under special conditions, consistently across an enormous and varied body of evidence. There's a simple way to picture why this might be true. Imagine two ways of caring for a young plant. In one, you pour an entire week's worth of water onto it all at once, on a single day. In the other, you give it a little water each day across that same week. The total amount of water is identical in both cases, but only one of these approaches actually helps the plant grow well, because growth needs time, and repeated, gentle attention, not one overwhelming dose. Studying seems to work in a remarkably similar way. A memory revisited across several separate days, with some forgetting allowed to happen quietly in between each review, seems to root itself more deeply than the same information reviewed the same number of times, back to back, in one long sitting the night before a test. It's a small, gentle piece of permission, in a way. The version of you who studies a little bit today and lets it rest, and studies a little more in a few days' time, isn't being lazy or inefficient. Research suggests that version of you may quietly be doing it exactly right. Let's turn next to a related question. How much can a mind actually hold on to at any one moment? Here's a habit most of us fall into without ever questioning it. When studying a particular kind of problem, we tend to practice that one kind over and over until it feels solid before moving on to the next kind. Researchers call this blocked practice, and on the surface, it seems like the obviously sensible way to learn. In 2007, researchers Doug Rohrer and Kelly Taylor decided to test this assumption directly, using college students learning to solve a particular category of math problem. Some students practiced problems in the usual blocked way, the same problem type, repeated in a row until moving on. Others practiced the very same problems in the very same total quantity, but shuffled one kind, then a different kind, then a third, mixed together rather than grouped. A week later, when everyone was tested, the difference wasn't subtle. The students who'd practiced with mixed shuffled problem sets substantially outperformed those who'd practiced one type at a time. What researchers now call interleaving had clearly outperformed blocking on exactly the same material in exactly the same amount of practice time. There's a nice, gentle explanation for why. When you drill the same problem type over and over, you don't just learn how to solve it. You're also, without realizing it, being handed a very large hint. You already know which method to use before you've even finished reading the question, because it's the only method you've been practicing for the last 10 minutes. Shuffle the problems, and suddenly each one asks you to first figure out what kind of problem it even is, before you can decide how to solve it. That extra step, quietly identifying the right tool for the job, turns out to be a genuinely important part of real learning, one that blocked practice lets you skip entirely. This same effect shows up somewhere rather more artistic. A researcher named Nate Cornell, working with Robert Bjork, ran a study using paintings by a set of relatively unfamiliar artists. Some participants studied each artist's paintings grouped together, several in a row. Others studied the very same paintings, interleaved, one artist's work, then another's, then a third's, shuffled throughout the session. Afterward, everyone was shown entirely new paintings and asked to guess which artist had created each one. The participants who'd studied the paintings interleaved were noticeably better at correctly identifying the artist's style on paintings they'd never seen before, even though, when asked beforehand which method they thought would work better, most participants confidently guessed the opposite. Grouping felt more organized, more effective, more like real studying. It simply wasn't. There's something quietly funny in that particular detail, if you sit with it. An entire room of people, having just performed noticeably better after mixing everything up, still walked away, feeling that keeping things neatly sorted must have been the better approach. Learning, it turns out, doesn't always feel like what it actually is. For our purposes tonight, the lesson sits comfortably alongside everything else we've wandered through. The version of studying that feels a little more chaotic, a little less tidy, is very often the version quietly doing more of the real work underneath. Here's a small, charming piece of science history worth knowing. In 1956, a psychologist named George Miller published a paper that would go on to become one of the most cited in the entire field, built around a single, oddly specific number, 7. Miller had noticed something curious across a wide range of unrelated experiments on human short-term memory. The number of separate items a person could reliably hold in mind at once, whether it was digits, words, or musical tones, tended to hover somewhere around 7, give or take a couple either way. Miller himself, in his own later writing, described feeling almost comically pursued by this number, as though it kept turning up uninvited across entirely different corners of his research, regardless of what he was actually trying to measure. It's a rare thing, a serious scientist openly admitting to feeling gently haunted by an integer, and it's the kind of detail that makes the history of psychology a little more human. What Miller's work pointed to is a real and useful limit. On its own, your short-term working memory can only hold a handful of separate, unconnected items before things start to blur and slip, which is part of why an unfamiliar phone number or a brand new password can feel surprisingly difficult to hold in mind for even a few seconds. But Miller also pointed to the workaround, one you very likely already use without ever having a name for it: chunking. If you group individual items into a smaller number of larger, meaningful units, you can hold far more information in mind at once. A string of 12 random digits is difficult to remember. The same 12 digits, grouped into 3 familiar-feeling chunks, becomes far more manageable. Not because your underlying capacity changed, but because you're now holding 3 things in mind instead of 12. It's a small, practical piece of design built right into how your mind organizes information, turning an awkward pile of separate pieces into a few larger, friendlier shapes. Now, here's where things get genuinely astonishing. It turns out even very young infants, long before they can chunk anything on purpose, are already remarkably good at finding patterns in a stream of information all on their own. In the mid-1990s, researchers Jenny Safran, Richard Aslan, and Alyssa Newport ran an experiment on 8-month-old infants that quietly reshaped how scientists think about the earliest stages of language learning. They created an entirely made-up language, strings of nonsense syllables, with no real words, no pauses between them, and no meaning whatsoever attached to any part of it. Just a continuous, unbroken stream of sound following certain statistical patterns. Some syllables simply tended to follow certain other syllables more often than pure chance would predict, the way real word boundaries tend to work in actual spoken language. The infants listened to this invented language for a grand total of about 2 minutes. Afterward, when tested, these 8-month-olds reliably distinguished between the syllable combinations that had followed the language's statistical patterns, the made-up words, in effect, and combinations that hadn't, made from syllables that had simply been placed next to each other by chance during testing. With no instruction, no reward, no one pointing anything out to them, and only 2 minutes of listening, these infants had extracted real structure from what was, to any outside observer, simply a wash of unfamiliar sound. It's genuinely difficult to overstate how remarkable this is. Long before a baby can speak a single recognizable word, long before they understand what a word even is, some quiet, powerful part of their mind is already doing sophisticated statistical work in the background, sorting signal from noise, finding pattern in what sounds, to the rest of us, like pure babble. There's a gently humbling thought in there somewhere, if you're willing to entertain it, while lying here in the dark. An 8-month-old, who cannot yet ask for a snack or hold up their own head for very long, is quietly outperforming most adults at a specific, elegant kind of pattern recognition, simply by listening. Learning, it turns out, doesn't always require explanation or effort or even conscious attention. Sometimes it just requires exposure and a mind quietly built to notice what repeats. And listening isn't the only quiet way we learn without being taught directly. Watching turns out to matter just as much. Long before children can read an instruction manual or follow a spoken explanation, they are already remarkably careful students of the people around them, constantly watching, absorbing, and quietly copying, often without anyone intending to teach them anything at all. This idea, that a great deal of learning happens simply through observation, without direct instruction or reward, was formally established through a series of studies in the early 1960s by the psychologist Albert Bandura and his colleagues, research that became foundational to what's now called social learning theory. Bandura's core finding, distilled to its gentlest form, was this: children reliably picked up behaviors simply by watching an adult perform them, even without being told to, and even without any reward for doing so. Observation alone was enough to plant a new behavior. This was, at the time, a genuinely significant shift in how psychologists thought about learning. Before Bandura's work, many theories focused heavily on direct reward and punishment as the primary engines of learning. You learned to do a thing because you were rewarded for it, or you learned to avoid a thing because you were punished. Bandura's research showed something quieter and, in its own way, more constant. Children are learning from you all the time, simply by watching, whether or not you're actively trying to teach them anything in that moment, which is, if you're a parent or an older sibling, or really anyone who spends time around children, a delightfully humbling thought to sit with. Kids have an uncanny, almost comedic talent for absorbing precisely the specific words, gestures, or habits you were quietly hoping they hadn't noticed, and repeating them back at the least convenient possible moment. But the underlying principle, stripped of its more amusing consequences, is a genuinely important one. Much of what any of us know, we never sat down and were formally taught. We picked it up sideways by watching someone else do it first. Which leads to one last question worth sitting with tonight. What actually makes us want to learn something in the first place? There's a particular kind of question that seems to unlock understanding in a way that simply reading an answer never quite manages. The question of why. Psychologists have studied a specific technique built entirely around this instinct. It's called elaborative interrogation, and it was formally investigated in a series of studies in the 1980s by researchers including Michael Presley and Mark McDaniel. The technique itself is almost disarmingly simple. While studying a fact, you pause and ask yourself why that fact would be true. And then you try to answer your own question, drawing on whatever you already know. In their studies, Presley and his colleagues found that people who generated their own explanations for facts they were studying, even fairly simple, self-guided explanations, remembered those facts substantially better afterward than people who had simply read the same facts without pausing to explain them. Here's a gentle example of what this actually looks like in practice. Imagine studying the fact that a particular bird migrates thousands of miles each year. Simply reading that sentence gives you a fact sitting alone, unconnected to anything else. But pause and ask yourself, why would a bird do that? And you're forced to reach for what you already know. Something about food availability changing with the seasons, something about warmth, about survival. And in doing that, reaching, the new fact gets quietly stitched into a web of things you already understood, rather than left floating by itself, easy to lose track of later. This appears to be the real mechanism behind why elaboration works so well. It's not really about the explanation itself being correct or complete. It's about the act of connecting new information to your existing knowledge, rather than letting it sit in isolation. A fact with no connections is remarkably easy to lose. A fact wired into several others you already know has far more paths leading back to it later. There's a rather charming, very human echo of this technique in something almost every adult has experienced from the other direction. A small child, somewhere around the age of 3 or 4, entering what parents sometimes call the why phase, greeting nearly every statement, however ordinary, with a patient, relentless, single-word question. Why is the sky blue? Why do we sleep? Why does the dog do that? It can be genuinely exhausting to sit on the receiving end of, late in a long day. But there's something worth quietly admiring in it too. That small, endlessly repeated question is, essentially, the exact same instinct researchers eventually built an entire evidence-based study technique around, just performed by someone too young to know they were doing science. The gentle takeaway, for tonight and for whatever you're studying next: reading a fact answers what? Pausing to ask yourself why tends to be what actually makes it stay. Here's a small experience you almost certainly recognize. A word sitting right at the edge of memory, refusing to surface. Or a story interrupted right before the ending. Something about that particular kind of not quite knowing produces a distinct, almost physical itch a pull toward resolving it that's hard to simply ignore. In 1994, a researcher named George Lowenstein proposed an elegant explanation for exactly this feeling in what's become known as the information gap theory of curiosity. His core idea was this: curiosity arises specifically at the moment we become aware of a gap between what we currently know and what we want to know. It isn't simply a vague, general love of learning. It's a sharp, specific response to noticing a particular hole in our own understanding, and that noticing is what creates the pull to fill it. This helps explain something that might otherwise seem strange. Why a single well-placed question can capture your attention far more powerfully than a whole page of interesting facts. A fact, on its own, doesn't create a gap. A question does. The moment you become aware of not knowing something you'd like to know, some part of your mind quietly, insistently, wants that gap closed. There's a small irony worth noting gently here near the end of a video that has spent this entire time deliberately avoiding cliffhangers, deliberately refusing to end any chapter on a note of suspense. The ordinary cliffhanger, the find out what happens next of a story or a mystery, has more genuine scientific backing behind it than most people probably realize. It works precisely because it opens a small, specific gap your mind wants closed. Tonight, though, we're doing the opposite on purpose. No gaps left open, no loose threads pulling at your attention. Just quiet, complete thoughts, one after another, asking nothing more of you than rest. Here's a small, quiet irony worth noticing, right about now, so late into a video built almost entirely out of narration and stillness. The very thing you're doing right now, listening to words while a slow, related image sits gently in front of you, is itself a demonstration of the research we're about to talk about. Researchers James Clark and Alan Pivio, in an influential 1991 review, described something called dual coding theory. The core idea is elegant, and once you hear it, almost obvious. Your mind seems to process and store verbal information, words, language, spoken explanation, somewhat separately from visual information, images, pictures, mental scenes. And when both are provided together, describing the same idea, they don't simply add up. They tend to reinforce each other, each pathway offering the mind another route back to the same memory later. This helps explain something researchers call the picture superiority effect. Across a wide range of studies, people tend to remember pictures more reliably than they remember the words used to describe those same things. Show someone a picture of a chair and later ask them to recall it, and they'll typically do better than if you'd simply told them the word chair. Give them both together, word and image, and the advantage tends to be stronger still. Two separate, complementary paths to the same memory rather than just one. It's a genuinely useful piece of research for anyone thinking about how to study, but it's worth sitting with gently rather than mechanically. Providing a picture alongside a fact doesn't automatically help. The image needs to actually relate to the idea being learned, rather than simply being decorative or worse, distracting. A beautiful, entirely unrelated picture placed next to an important concept can quietly steal attention away from the very thing it was meant to support. The benefit comes specifically from a relevant image reinforcing a relevant idea, not from images in general. There's something rather nice about ending tonight's wander through the science of learning on this particular finding, given the shape of the video you've been listening to. Nearly every idea we've talked about tonight has arrived paired with some kind of quiet, slow-moving image, not because it makes the video prettier, though hopefully it does, but because, according to Clark and Pivio's own research, Giving your mind two gentle paths to the same idea rather than one is genuinely more likely to help it stay. Which means, in a small and rather fitting way, this video has been trying to teach you the way it works best the whole time, without ever quite mentioning it until now. And so, we come to the end of tonight's slow walk through the quiet mechanics of learning itself. We've met a group of ordinary volunteers who, without fully realizing it, physically reshaped a small part of their own brains simply by learning to juggle. We've learned that testing yourself, however uncomfortable it feels in the moment, tends to outlast the false comfort of rereading. We've spent a little time with Hermann Ebbinghaus, alone with his invented nonsense syllables, patiently mapping how forgetting actually behaves. We've pictured a plant, watered a little at a time, rather than all at once, and let that stand in for how spaced out studying seems to work. We've met a psychologist gently, almost comically haunted by the number 7. We've marveled a little at an 8-month-old quietly finding pattern in 2 minutes of nonsense sound. We've thought about how much of what we know we simply picked up by watching someone else first. And we've sat, for a moment, with a small itch of an unfinished thought, and what that itch reveals about why curiosity pulls at us the way it does. None of it requires you to remember a single name or study right now. Your own brain, gently and without being asked, is perfectly capable of sorting through tonight's chapters on its own terms, keeping whatever quietly turns out to matter, and letting the rest drift away, exactly as it's supposed to. If tonight helped you unwind a little, a like or a subscribe helps someone else find their way here too. Wherever you are, whatever you're learning right now, in this stage of your life, your brain already knows how to do this. It always has. Sleep well, rest easy, and good night.